Libya, November 28, 1941. In the pre-dawn darkness near Sidi Rezeg, a British machine gun crew of the 2nd Battalion, Cheshire Regiment, waited on a rocky ridgeline as temperatures hovered near 40 degrees Celsius. The North African desert offered no comfort. Dust had already infiltrated every mechanism, every breathing space, coating the crew's uniforms and equipment with a fine, abrasive powder. The crew sergeant, a veteran of 3 years' service, methodically checked his water cans by touch in the darkness. 7 pints in the cooling jacket, another 14 in reserve containers, plus the rubberized steam recovery apparatus that would prove crucial in the hours ahead. A radio message crackled from battalion headquarters through the unit's wireless set. Enemy movement detected approaching from the west. Sustained fire authorized upon visual contact. Commanders at brigade level had expected sporadic engagement, perhaps 15 to 20 minutes of suppression fire against reconnaissance patrols. But the intelligence reports arriving that morning told a different story. Entire columns of German armor from the 21st Panzer Division probing for weak points in the Commonwealth defensive line, requiring hours of continuous interdiction, not brief minutes of harassment. The Vickers gun, Mark I, fed by cotton ammunition belts and cooled by the recirculating water system that defined its design philosophy, sat silent but fully prepared on its tripod mount. What followed in the next 8 hours would demonstrate a principle that industrial warfare had begun to encode into military doctrine. In prolonged combat operations, continuity defeats intensity, endurance trumps burst performance, and systematic preparation overcomes momentary superiority. London, June 24, 1912. A War Office memorandum confirmed adoption of the Vickers .303-inch machine gun, a refined evolution of Hiram Maxim's original automatic weapon that had revolutionized infantry firepower 3 decades earlier. The modifications undertaken by Vickers, Sons and Maxim Limited were systematic and methodical. A lighter receiver constructed from high-tensile steel, a locked breech toggle mechanism that provided reliable operation with reduced weight, and most significantly, a water jacket holding approximately 7 pints, roughly 3.3 liters, of cooling fluid surrounding the barrel. Engineering specifications documented in early service manuals established heat management as a calculated variable rather than an uncontrolled risk. The gun could sustain approximately 600 rounds of continuous fire before the water reached boiling point at 100 degrees Celsius, or 212 degrees Fahrenheit. Evaporation occurred at a predictable rate that had been measured through extensive trials. 1.5 pints per 1,000 rounds fired under standard conditions. These figures were not rough estimates or theoretical projections. They were measured data points, derived from controlled trials conducted at government testing facilities, and codified into training regimens at the Small Arms School at Hythe in Kent and the Machine Gun School at Netheravon in Wiltshire. Instructors drilled crews on stoppage clearance procedures, ammunition belt handling techniques, and most critically, systematic water management protocols. The gun's service reputation throughout the British Army became encapsulated in the phrase reliable if maintained to tables, a concise expression that captured the weapon's engineering philosophy. Reliability was not an inherent property that could be assumed. It was earned through adherence to documented maintenance schedules, proper cleaning procedures, and respect for operating parameters. A crew that followed procedures would have a functioning weapon. A crew that neglected maintenance would face stoppages and failures. During the Great War of 1914 to 1918, the Vickers evolved beyond its original conception as a direct-fire weapon supporting infantry advances. British forces began employing it for indirect fire missions, plotted, map-based barrages that resembled light artillery operations more than traditional machine gun employment. This doctrinal evolution reflected both the weapon's technical capabilities and the tactical realities of trench warfare. The most extensively documented example occurred at High Wood during the Somme offensive, specifically on the night of August 23 to 24, 1916. 10 guns of the 100th Machine Gun Company, operating in carefully prepared positions with overhead firing arcs, delivered approximately 1 million rounds over 12 continuous hours into German-held areas at ranges exceeding 2,000 yards. Modern historical analysis, drawing on both British and German archival sources, has reconstructed the logistics of that operation in remarkable detail. The quantity of ammunition transported forward by supply trains and carrying parties, measured in tons, the water consumption and resupply schedules that maintained cooling system operations, the barrel maintenance procedures including periodic inspection and replacement when rifling where reached acceptable limits, and the crew rotation systems that prevented fatigue-induced errors during the marathon firing mission. The achievement was not merely one of mechanical endurance, though the guns themselves performed admirably, but demonstrated organizational capacity. The ability to coordinate ammunition supply across miles of communication trenches, to maintain water resupply despite enemy counter-battery fire, to rotate gun crews to prevent exhaustion, and to sustain fire control discipline across multiple weapons and many hours. By 1918, as the Western Front transitioned from static trench warfare to more mobile operations, British General Staff were publishing machine gun fire tables with the mathematical rigor and attention to detail typically reserved for field artillery gunnery calculations. Range cards specified elevation angles for various target distances, taking into account factors like ammunition temperature, barrel wear, and atmospheric conditions. Beaten zone calculations mapped the dispersion pattern of bullets over different ranges and terrains. Fire control procedures established communication protocols between observers and gun crews. An archival fragment from a Vickers technical data sheet of the period reads with bureaucratic precision: capacity of barrel casing 7 pints. Number of rounds required to boil water 600 rounds of continuous firing. Rate of evaporation 1.5 pints per 1,000 rounds. These numbers were not tactical suggestions subject to interpretation. They were engineering constraints that shaped operational doctrine, influenced tactical planning, and determined what missions could be executed with available resources. Netheravon, May 1937. At the Machine Gun School, instructors plotted beaten zones and overhead fire trajectories on 1 to 25,000 scale maps. The interwar British Army had formalized a concept. The Vickers was not a squad centerpiece but an area fire support system. This doctrinal shift was documented in training pamphlets, particularly Small Arms Training Volume 1, Infantry Section 1, Part 3-1, commonly referenced as SS-131 in period correspondence. The manual enforced controlled firing rates. Practical rate of fire was set at 250 rounds per minute, well below the mechanical cyclic rate of 450 to 500 rounds per minute. This deliberate reduction served multiple purposes. It extended barrel life, conserved ammunition, and most importantly, allowed sustainable heat dissipation. Water management procedures were standardized using condenser bags and recovery cans. Period equipment lists specified capacity ranges of 6 to 7 pints for the jacket cooling system, with detailed instructions for steam recovery via rubberized condensing bags and tubing adapters. The organizational structure reflected this philosophy. The British Army formed dedicated machine gun battalions whose primary function was to mass fire in a manner analogous to light artillery. Multiple guns could be coordinated to deliver overlapping fire patterns across terrain features, creating sustained suppression over hours rather than minutes. This approach persisted into the Italian campaign of 1944, where machine gun battalions operated as semi-independent fire units with their own logistics and command structures. The contrast with other armies' assumptions was stark. Many military forces presumed that air-cooled machine guns could surge through heavy engagement tasks by accepting temporary overheating. British staff planning, however, operated on different principles. They designed for hours-long missions with predictable heating curves and planned resupply. On the eve of the Second World War in September 1939, the British Army had standardized more machine gun firing tables than some formations maintained for their light artillery pieces. This was a deliberate institutional bet on endurance fire. Berlin, March 1942. The Heereswaffenamt, the German Army Weapons Agency, finalized specifications for the MG-42 machine gun, officially the Maskeningewehre 42. The weapon represented a fundamentally different design philosophy. Where the Vickers emphasized sustained output through water cooling, the MG-42 achieved tactical dominance through extraordinary cyclic rates of fire, approximately 1,200 to 1,500 rounds per minute. This was nearly triple the Vickers practical rate. The engineering trade-offs were explicit. German doctrine emphasized quick-change barrel systems as the primary heat management solution. Training manuals and post-war museum technical analyses describe barrel swaps occurring as frequently as every 200 to 250 rounds under continuous firing conditions. Gun crews carried multiple spare barrels and a specialized barrel carrier, the Laufschützer, designed to hold hot barrels during cooling intervals. The barrel change process itself was rapid, typically completed in under 10 seconds by trained crews, but it represented an interruption in fire nonetheless. The sound signature of the MG42 became infamous among Allied soldiers, who nicknamed it the buzzsaw or Hitler's zipper due to its distinctive high-rate tearing noise. In short bursts, the weapon was devastating. The psychological impact of such intense fire concentration could suppress enemy movement within seconds. However, the physical reality of heat generation imposed tactical constraints. Extended firing required not just ammunition resupply but barrel inventory management, a logistical burden distinct from, but comparable to, the Vickers water requirements. British intelligence analysts studying captured MG42 weapons and prisoner interrogations began to frame the design contrast in systematic terms: intensity versus continuity. The German approach accepted heat-driven firing pauses in exchange for devastating burst capability. The British approach sacrificed burst intensity for uninterrupted endurance. Late-war German units operating in defensive positions had to budget operational time not just for ammunition supply but for barrel availability. A company might allocate barrel hours the way other formations allocated artillery tubes. Meanwhile, British Vickers teams budgeted water, a different logistical challenge with different tactical implications. Neither approach was inherently superior. Each reflected national industrial capabilities, tactical doctrine, and operational requirements. Cyrenaica, Libya, November 1941. Operation Crusader, the British Eighth Army's ambitious offensive to relieve the besieged garrison at Tobruk and drive Axis forces from eastern Libya, placed enormous demands on Commonwealth machine gun units. The 2nd Battalion, Cheshire Regiment established Vickers sections on commanding ridgelines near Sidi Rezegh, positions that offered excellent fields of fire across the approaches but exposed gun crews to the harsh environmental conditions of desert warfare. The terrain offered commanding ridgelines but exposed gun crews to extreme environmental stress that tested both equipment and personnel. Daytime temperatures regularly exceeded 40 degrees Celsius, approximately 104 degrees Fahrenheit, while nights could drop below freezing. Dust was omnipresent, a fine powder that infiltrated optical sights, fouled mechanisms, abraded moving parts, and coated every surface with a gritty film that required constant cleaning to maintain weapon functionality. Water was precious for all purposes in desert operations: drinking, cooking, washing, vehicle cooling. Yet machine gun operations demanded substantial quantities specifically for weapons cooling, creating competing demands on limited supply systems. Vickers crews implemented field modifications to standard water management procedures, adapting peacetime training to combat realities. They connected rubber hoses from the gun's steam outlet valve to improvised condenser cans, often fabricated from petrol tins or salvaged containers, creating recovery systems that captured evaporating water for reuse. The condensing process was surprisingly effective. Under optimal conditions, crews could recover 60 to 70% of evaporated steam, though dust contamination and imperfect seals reduced efficiency in field conditions. Still, even 50% recovery represented a significant operational advantage when water resupply was uncertain. Ammunition arrived from forward supply dumps via 1,500-weight trucks, light military cargo vehicles that navigated the treacherous desert tracks connecting rear echelon depots to frontline positions. The ammunition was transported in pre-linked cotton belts housed in wooden boxes or, increasingly by late 1941, metal containers that better resisted the sand and dust. Each box contained 250 rounds in a single belt, though longer belts could be assembled by linking multiple standard belts together using special connecting clips. Daily ammunition consumption for a company-sized unit engaged in active defensive operations could reach tens of thousands of rounds, straining supply systems already stretched thin supporting armored formations and artillery batteries. Battalion war diaries and contemporary training estimates suggested average figures around 10,000 rounds per gun per day during heavy engagement periods, though specific consumption varied dramatically by mission intensity, target availability, and tactical situation. Some positions in exposed sectors might fire 30,000 rounds in 24 hours, while others in quieter areas might fire only hundreds. The tactical pattern that emerged during Operation Crusader favored sustained harassment fire rather than brief, decisive suppression. This reflected both the weapon's technical capabilities and the operational realities of desert warfare, where enemy forces often operated in dispersed columns rather than concentrated formations. German and Italian forces moving during dawn or dusk, the cooler portions of the day when visibility improved but heat stress decreased, encountered Vickers fire that continued hour after hour with mechanical consistency. Air-cooled weapons could match this output in brief intervals, perhaps 5 to 10 minutes of intense fire before barrel temperatures forced a pause or barrel change. But the Vickers sections, with their water-cooled barrels and systematic ammunition supply, maintained output across multiple hours, fundamentally shaping enemy movement patterns and operational timings. German commanders, reviewing after-action reports and prisoner interrogations, noted in intelligence summaries that British machine gun positions could not be easily suppressed through counter-battery fire because the guns often displaced after extended firing missions, having depleted local ammunition stocks rather than experiencing mechanical failure or heat force pauses. The logistics of desert warfare imposed severe constraints on all units regardless of nationality or technical superiority. British supply chains struggled to move petrol for vehicles across hundreds of miles of desert tracks, water for personnel in a climate that could kill through dehydration in hours, and ammunition for all weapon systems from rifles to heavy artillery. German and Italian forces faced even more severe logistics challenges, particularly after Allied naval and air forces interdicted Mediterranean shipping lanes supplying Axis forces in North Africa. Yet within this framework of universal scarcity, British Vickers logistics included specialized equipment for steam reclamation that demonstrated systematic planning. Documented supply lists reference bag, condenser, steam, along with brass adapters, rubber tubing, and protective canvas covers, formalized equipment with designated stock numbers, established distribution schedules, and inclusion in standard machine gun section equipment tables. The marginal efficiency gain from water recovery might appear trivial when viewed from a strategic level, but at the tactical level of a gun section operating in an exposed forward position, it meant the difference between continuing to fire after sunset when resupply trucks had withdrawn to protected areas or falling silent when water reserves depleted. This capability translated directly to operational effectiveness and tactical flexibility. Port said, Egypt, February 1942. Royal Army Ordnance Corps workshops in the rear areas conducted systematic evaluations of weapons performance under desert conditions. Engineers tested the hypothesis that water cooling provided measurable advantages in prolonged engagement scenarios. The data validated theoretical predictions. With 7 pints of water in the cooling jacket, the Vickers absorbed heat that would otherwise cause rapid rifling erosion in air-cooled barrels. The condensing kits in use could reclaim a substantial fraction of evaporated water. Estimates suggested recovery rates of 60 to 70% under optimal conditions. Technical data sheets specified precise performance parameters. 600 rounds of continuous fire would bring the cooling water to boiling point at 100 degrees Celsius, or 212 degrees Fahrenheit. Evaporation rate was measured at 1.5 pints per 1,000 rounds fired. These figures allowed staff officers to compute water carriage requirements versus expected mission duration. A section equipped with 21 pints of water, 3 full jackets worth, could theoretically sustain fire for 8,400 rounds before requiring external resupply, assuming perfect recovery from the condensers. In practice, accounting for spillage, contamination, and incomplete recovery, the realistic figure was lower, perhaps 6,000 rounds, but still substantial. The contrast with air-cooled systems became apparent in comparative trials. An air-cooled machine gun operating without barrel changes could fire approximately 200 to 250 rounds before requiring a cooling pause. With prepositioned spare barrels, a well-trained crew could extend this capacity through rapid barrel changes, but each change represented a tactical interruption and required crew exposure to remove and replace the hot component. Under matched load conditions, both weapons firing equivalent total round counts over equivalent time spans, the Vickers demonstrated superior barrel longevity and dispersion stability. Rifling where progressed more slowly because the barrel temperature never approached the extreme peaks experienced by air-cooled weapons. The implication for operational planning was significant. Remote observation posts or forward defensive positions equipped with Vickers guns could maintain fire throughout night-long engagements with minimal external support, provided they had been pre-stocked with ammunition and water. The water requirement, while non-trivial, could be met through diverse sources. Canteens, captured supplies, even collected rainwater or condensation in some environments. The psychological effect on opposing forces was documented in prisoner interrogations. German soldiers reported that British machine gun positions seemed to never stop firing, creating an impression of limitless ammunition reserves. The reality was more prosaic, not limitless ammunition, but limited by logistics rather than mechanical constraints. The historical record preserves two frequently conflated data points, both remarkable in their own right but distinct in their implications and contexts. Understanding the difference between these events is essential to accurate historical analysis. The first, Highwood, France, August 23 to 24, 1916, during the Great War's Somme offensive. 10 guns of the 100th Machine Gun Company, British Machine Gun Corps, operating in carefully prepared indirect fire positions with precisely calculated elevation and deflection settings, delivered approximately 1 million rounds over 12 continuous hours into German-held territory. This achievement demonstrated organizational capacity at the battalion and brigade level, the ability to coordinate ammunition supply across miles of communication trenches under artillery fire, gun crew rotation to prevent fatigue, water resupply using carrying parties and dedicated logistics personnel, and most critically, fire control discipline that maintains sustained fire patterns hour after hour. Modern scholarship, drawing on both British unit war diaries and German defensive reports, has analyzed the operation's logistics in exhaustive detail. The quantity of .303-inch ammunition transported forward measured in tons, requiring hundreds of men in carrying parties. The water consumption and resupply schedules that maintained cooling system operations at 10 gun positions simultaneously, and the barrel maintenance procedures including periodic inspection, cleaning, and replacement when rifling where reached critical thresholds that would degrade accuracy beyond acceptable limits. The second data point occurred decades later in a completely different context. Strensall, England, May 1963. The British Army, seeking to establish definitive mechanical reliability data for weapons in its inventory, conducted a controlled endurance trial at its testing ranges in Yorkshire. A single Vickers gun, selected randomly from existing stocks rather than being specially prepared, fired 5 million rounds over 7 continuous days, 168 hours, of sustained operation. The test protocol, documented in official reports that have since been analyzed by firearms historians and military technical experts, included scheduled barrel changes where measurements reached predetermined limits based on bore erosion and rifling degradation, mandatory crew rotation every few hours to prevent fatigue-induced errors in procedure, and constant monitoring and recording of all mechanical systems including the recoil mechanism, feed system, firing mechanism, and cooling. Jacket integrity. No terminal mechanical failure occurred during the entire week-long test. The gun continued to function at the end of the trial. The limiting factors that eventually ended the test proved to be consumable components, barrels worn beyond acceptable accuracy standards, ammunition belt fabric showing stress fatigue, and cooling water requiring replacement due to mineral buildup, not failure of the receiver mechanism, toggle system, or any other core components of the weapon itself. Popular retellings of Vickers' history have sometimes conflated these two events or misattributed the 7-day test to a wartime North African scenario, perhaps mentally connecting the weapon's documented desert service record with the impressive endurance trial data. The confusion is historically understandable given the Vickers' extensive and successful employment in the Western Desert campaigns of 1940 to 1943, where it performed admirably under harsh environmental conditions. However, the archival evidence from multiple sources, British Army official test reports, contemporary firearms technical publications, and unit histories is unambiguous and consistent. The 1963 test was conducted at Strensall under controlled conditions specifically designed to isolate mechanical reliability from tactical variables like enemy fire, supply disruption, crew casualties, and environmental extremes. The test environment allowed precise measurement and documentation that would be impossible in combat conditions. The distinction between high wood and Strensall matters not merely for historical accuracy, but because each event illustrates different aspects of the weapon's capability and the systems supporting it. High wood demonstrated mass application in combat conditions, the integration of weapons, logistics, training, and doctrine to achieve tactical effects against a determined enemy. It showed what a machine gun company could accomplish when properly supplied, commanded, and employed according to contemporary doctrine. Strensall demonstrated inherent mechanical endurance under laboratory-like control, the weapon's engineering robustness when isolated from external factors. It established baseline reliability data that informed subsequent weapons development and procurement decisions. Both achievements are significant. Neither should be minimized or confused with the other. Technical historians and firearms experts who have examined both events in detail note a consistent theme running through Vickers' employment from 1912 through its retirement from British service in the 1960s. When measured under rigorous conditions, whether combat operations or controlled trials, the weapon's limiting factor was consistently external rather than internal. Constraints were ammunition supply, barrel wear rates, water availability, and crew endurance, never receiver mechanism reliability, toggle system fragility, or spontaneous mechanical failure of core components. This engineering characteristic, achieved through conservative design tolerances, high-quality manufacturing standards, and extensive pre-service testing, shaped fundamentally how the weapon was employed throughout its service life. Doctrine assumed the gun would function if supplied with ammunition and water. Therefore, tactical planning focused intensively on logistics rather than mechanical backup or contingency positioning. Unlike weapons systems where mechanical failure was a probabilistic concern requiring redundant gun positions, multiple spares, or complex maintenance schedules, the Vickers could be treated as a reliable platform whose output was bounded primarily by supply chain capacity and crew stamina, not by fears of internal mechanical fragility or unpredictable breakdown. This reliability became so thoroughly assumed in British Army culture that it was often taken for granted rather than explicitly acknowledged. Yet it represented a significant tactical advantage that enabled sustained fire doctrines that would have been impossibly risky with less reliable weapon systems. Enfidaville, Tunisia, April 1943. German defensive positions in the final stages of the North African campaign relied heavily on the MG-34 and MG-42 machine guns for area denial. Unit after-action reports and post-war analytical syntheses reveal the tactical reality behind the weapon's fearsome reputation. In short bursts, the MG-42 was devastatingly effective. Its 1,200 to 1,500 rounds per minute cyclic rate could saturate a target area within seconds, creating immediate suppression that halted Allied infantry advances. However, sustained defensive missions exposed the weapon's heat management constraints. German doctrine codified barrel change procedures as routine, not exceptional. Training emphasized that barrel changes could be required as frequently as every 200 to 250 rounds during continuous engagement. Crews carried multiple spare barrels as standard equipment, along with insulated handling mitts and the Lofschützer barrel carrier for cooling hot tubes safely. The barrel change itself was rapid. German gun teams prided themselves on speed, but it represented a vulnerability window. During the 5 to 10 seconds required to swap barrels, the gun was out of action. Additionally, the physical characteristics of a hot barrel created secondary tactical concerns. Glowing metal was visible in darkness, potentially revealing gun positions to enemy observers or snipers. Steam and heat shimmer from recent firing could likewise betray locations. German units developed techniques to mitigate these signatures, positioning guns in defilade, using multiple firing points with coordinated displacement, but the fundamental constraint remained. Extended firing missions required not just ammunition discipline but barrel inventory management. Post-war analysis by British and American intelligence staffs framed the contrast in operational terms. The MG-42's rate of fire could suppress quickly, ideal for mobile defensive tactics and counterattack support. The Vickers continuity could suppress predictably over patrol windows and counterattack preparation cycles. In defensive positions where German units needed to interdict Allied movement over 6 to 8-hour night periods, the barrel logistics became a recurring constraint. Companies had to rotate gun teams not just for crew rest but to manage barrel temperature cycles. This was not a fault of German engineering or training, it was an inherent consequence of air cooling's physics applied to sustained fire missions. Monte Cassino and the Liri Valley, Italy, May 1944. The Italian campaign's mountainous terrain created ideal conditions for indirect machine gun fire. Commonwealth machine gun battalions, including Canadian formations, plotted Vickers fire onto approach roads, valley bottoms, and suspected assembly areas using the same map-based techniques developed during the Great War. Effective ranges extended to approximately 2,800 yards, nearly 2.6 kilometers, when firing at high angles across valleys. German observers monitoring these fire missions sometimes misidentified the source, attributing the sustained harassment to light artillery rather than machine guns. The mistake was understandable. Artillery and machine gun fire both delivered plunging trajectories. Distinguishing them required either direct observation or careful analysis of the sound signatures and impact patterns. The key difference was sustainability. Artillery tubes had limited barrel life and required significant logistical support for propellant and shells. Vickers guns, firing rifle-caliber ammunition, could sustain night-long missions with ammunition resupply that was feasible even on narrow mountain roads. Water management in the Italian theater presented different challenges than desert operations. Rather than water scarcity, crews dealt with mud, cold, and prolonged vibration from extended firing. The condensing equipment proved valuable in wet conditions, preventing steam clouds that might reveal positions to enemy observation posts. Crews collected rainwater to supplement issued supplies, demonstrating the system's flexibility. The Vickers' tolerance for water quality variations, it could operate with muddy or mineral-heavy water provided the jacket didn't freeze, made it adaptable to diverse field conditions. The tactical impact manifested in German after-action reports and prisoner statements. Commonwealth defensive positions employing Vickers harassment fire could disrupt German counterattack timings. German staff planning assumed that Allied positions would have predictable lulls when automatic weapons cooled or crews rotated. Vickers sections holding curtain fire patterns for 6 to 8 hours challenged these assumptions. In specific defensive cycles documented in unit histories, a single Vickers section's sustained ammunition expenditure exceeded what several dispersed MG-42 teams could deliver without heat-mandated pauses. The doctrinal contrast, British emphasis on continuous area interdiction versus German emphasis on mobile burst suppression, expressed itself in measurable operational differences. River Sangro, Italy, December 1943. 10th Corps, a formation of British 8th Army, prepared a crossing operation against German defensive positions on the far bank. The fire support plan included a novel element, a machine gun barrage employing dozens of Vickers guns coordinated to deliver time-controlled suppressive fire across designated zones. The concept extended the indirect fire techniques developed during the Great War to an operational scale. Multiple machine gun companies from different battalions synchronized their fire to create overlapping beaten zones that denied movement across the river approaches and nearbank areas. Historical analyses of the Sangro operation compared the suppressive effect to light artillery, but at dramatically different resource costs. Artillery barrages consumed propellant charges and high-explosive shells, both of which stressed logistic systems and degraded gun tubes relatively quickly. The machine gun barrage consumed rifle-caliber ammunition, which was produced in vastly greater quantities and imposed less wear on weapon systems. A staff calculation from the period illustrated the industrial dimension. The total ammunition expenditure for a typical machine gun barrage might equal one day's output from a single Royal Ordnance Factory rifle-caliber production line. The contrast with artillery ammunition production was stark. Achieving equivalent suppression through artillery would require substantially more industrial capacity and logistics overhead. The tactical execution required precise timing and coordination. Gun crews operated from firing tables that specified elevation, azimuth, and timing for each belt fired. The effect was not precision interdiction but area denial, making terrain hazardous enough that movement across it became prohibitively risky. Operational research studies conducted after the Sangro crossing concluded that planned Vickers barrages could deliver predictable suppression over mapped zones comparable to light artillery, provided that ammunition supply chains were synchronized with fire missions. The key phrase was predictable. The output was calculable based on gun numbers, ammunition stocks, and firing durations. The Germans adapted to this tactic through timing adjustments and route selection, but adaptation required intelligence about Commonwealth machine gun positions and firing schedules. The organizational resilience of the British system, with dedicated machine gun battalions operating semi-independently, meant that suppressing the barrage required counter-battery fire against dispersed, dug-in positions rather than concentrated artillery parks. The exchange ratio favored the defender in this scenario. One Vickers position might require multiple artillery missions to neutralize, while the machine gun could resume firing once the counter-battery fire shifted. Northern Apennines, Italy, September 1944. The Gothic Line, officially known to German forces as the Gotenstellung, represented one of the Second World War's most formidable defensive positions, a carefully engineered series of fortifications stretching across northern Italy from the Ligurian Sea to the Adriatic coast. German engineers had spent months constructing concrete bunkers, anti-tank ditches, minefields, and interlocking fields of fire that exploited the mountainous terrain to maximum defensive advantage. Commonwealth forces attacking these positions encountered sustained German resistance that required continuous suppression to enable infantry movement through the kill zones. British and Canadian machine gun battalions supporting the offensive conducted missions spanning 36 hours or more without interruption. Harassing fire during German rest periods to prevent recuperation, final protective lines positioned to interdict counterattacks before they could develop momentum, and beaten zone curtains carefully plotted on maps and keyed to likely assembly areas identified through signal intelligence, prisoner interrogations, and aerial reconnaissance photography. German tactical intercepts, radio communications decoded by Allied signals intelligence units, and prisoner interrogations conducted at forward interrogation posts, compiled systematically in Allied psychological warfare summaries and intelligence bulletins, revealed a recurring impression among German soldiers defending the Gothic Line, that Commonwealth machine guns do not stop. This perception was not literal truth in the sense of literally continuous fire without any pauses. Guns ceased fire for tactical reasons including target unavailability, crew changes to prevent fatigue-induced errors, ammunition resupply operations that required brief interruptions, and repositioning to alternate firing positions when German counter-battery fire became too accurate. However, the perception reflected an operational reality that had significant psychological and tactical implications. Vickers sections, when supplied with sufficient ammunition stockpiles and adequate water reserves, could maintain intermittent fire across entire nights. Darkness hours stretching from dusk around 1800 hours to dawn around 0600 hours, approximately 12 continuous hours of availability for fire missions. German infantry planning, which had been developed based on experienced fighting forces equipped with air-cooled machine guns, had to be fundamentally revised to account for continuous interdiction rather than cyclic suppression with predictable gaps that could be exploited for movement. The industrial dimension becomes particularly relevant when examining Gothic Line operations in their broader strategic context. Monthly ammunition production and distribution reports from British logistics commands, preserved in the National Archives, show Allied industry sustaining weeks of intensive machine gun operations across the Italian front without supply shortages or rationing requirements. Production of .303-inch ammunition from Royal Ordnance factories in Britain, supplemented by Commonwealth production in Canada, Australia, India, and South Africa, exceeded consumption even during peak offensive periods when tens of millions of rounds were expended monthly. The logistics system could deliver ammunition forward faster than machine gun battalions could fire it, an industrial capacity advantage that translated directly into tactical flexibility. In stark contrast, German ordnance summaries from the corresponding period discuss in detail the barrel allocation policies necessary for MG weapons deployed in static defensive sectors across multiple fronts. German units had to ration barrel hours, the cumulative firing time before a barrel required replacement due to rifling erosion, the same way artillery formations ration tube life for their field guns and howitzers. This barrel constraint did not prevent effective German defensive fire. German machine gun crews continued to demonstrate high tactical proficiency and extracted maximum performance from their weapons throughout the Italian campaign, but it influenced tactical planning at company and battalion levels in subtle but significant ways. Company commanders had to balance immediate suppression needs against long-term barrel inventory management, sometimes accepting tactical disadvantages in the present to preserve barrel life for anticipated future engagements. Replacement barrels were allocated through formal requisition systems that competed with other critical supply needs including ammunition, fuel, vehicle spare parts, and winter clothing. Units in contact with the enemy received priority allocations, but even then, replacement schedules might lag behind consumption rates during intensive defensive battles. Some German units reported improvising local solutions, including collecting barrels from destroyed weapons, establishing unit-level barrel repair workshops that attempted to extend barrel life beyond normal replacement intervals, and rotating barrels between multiple weapons to distribute wear. These adaptations demonstrated tactical ingenuity and maintenance excellence, but they also indicated fundamental supply constraints that Allied forces, with their superior industrial base and secure logistics chains, did not face to the same degree. The contrast in operational tempo and tactical flexibility illustrates how different doctrinal approaches to sustained combat emerged from different national circumstances, industrial capabilities, and historical experiences. German squad-level tactics, refined through years of mobile warfare on the Eastern Front and in North Africa, emphasized mobile defense with intense, devastating fire applied at critical moments to disrupt enemy attacks, break up formations, and create opportunities for counterattack. This doctrinal approach required weapons that could deliver overwhelming bursts of fire, which the MG-42 certainly provided with its extraordinary cyclic rate. British battalion-level tactics, developed through experience in the Great War and refined during the Second World War, emphasized continuous pressure through systematic fire planning, coordinated across multiple weapons and synchronized with artillery support and infantry movements. This approach required weapons that could maintain output across shifts and extended missions, which the Vickers provided through its water cooling system and mechanical reliability. Neither system was universally superior across all tactical scenarios. Effectiveness depended on specific mission requirements, available terrain, logistics support, and enemy dispositions. But in the attritional warfare of the Italian campaign, where Allied material advantages could be systematically applied over months-long operations, and where the mountainous terrain favored prepared defensive positions requiring sustained suppression, the endurance-focused British approach aligned well with operational realities and strategic objectives. By 1945, the accumulated data from 3 years of combat across multiple theaters allowed systematic comparison. British, American, and German staff analyses examined machine gun effectiveness through the lens of quantitative metrics. Rounds fired per barrel life, ammunition expenditure per casualty inflicted, logistics burden per sustained fire hour, and mechanical reliability rates under varied conditions. The Vickers emerged with a distinctive profile. Not the most mobile weapon, not the highest rate of fire, but the most consistent performer in sustained fire roles. The engineering data validated design decisions made 3 decades earlier. Water cooling, despite adding weight and complexity, proved its value in scenarios requiring uninterrupted fire. The 7-pint water jacket absorbed heat that would otherwise necessitate barrel changes every few hundred rounds. The practical effect was measurable. A Vickers section could deliver 5,000 to 6,000 rounds without barrel replacement, where an MG-42 team might require 5 to 6 barrel changes for equivalent output. Each barrel change represented time, crew exposure, and logistics burden. The ammunition consumption data revealed another dimension. British formations, employing Vickers guns in indirect fire roles, expended vast quantities of .303-inch ammunition. A typical night harassment mission might consume 10,000 rounds per gun. Across multiple battalions, monthly expenditure reached millions of rounds. Yet this was sustainable because rifle-caliber ammunition production was measured in billions of rounds annually. German ammunition production faced greater constraints, particularly in the war's final years, but more significantly, German barrel production for air-cooled machine guns became a limiting factor. Replacing worn barrels required manufacturing capacity that competed with other weapons production. The culminating assessment from Allied operational research sections emphasized system-level thinking. The Vickers was not merely a weapon but a component of a fire support system that included ammunition production, logistics infrastructure, training establishments, and tactical doctrine. Its effectiveness derived not from any single technical parameter but from the integrated performance across all these elements. German post-war analyses reached similar conclusions about the MG-42. Its tactical superiority in mobile operations was undeniable, but its employment in static defensive roles exposed limitations that were fundamentally about industrial capacity and logistics, not weapon design per se. The numbers, assembled and analyzed after the war, spoke to a larger truth: that weapons effectiveness is context-dependent and system-integrated, not merely a function of technical specifications. The comparative history of the Vickers and MG-42 machine guns illuminates fundamental questions about weapon design philosophy, military doctrine development, industrial capacity constraints, and the complex relationship between technology and warfare. Both weapons were engineered responses to genuine tactical requirements identified through combat experience and doctrinal analysis. Both reflected their respective nations' industrial capabilities, manufacturing traditions, resource availability, and operational priorities shaped by geography, strategic position, and military history. Neither was objectively superior across all tactical scenarios. Effectiveness was always context-dependent, shaped by mission requirements, terrain characteristics, logistics support, enemy capabilities, and countless other variables that defy simple comparison. The Vickers, with its water-cooled barrel system requiring 7 pints of cooling fluid and its moderate rate of fire averaging 250 rounds per minute in practical employment, excelled in sustained suppression roles where continuity of output mattered more than instantaneous burst intensity. Its ability to maintain fire for hours without forced cooling pauses or mandatory barrel changes made it ideally suited for defensive positions requiring continuous interdiction, indirect fire missions resembling light artillery, and situations where logistics could preposition sufficient ammunition and water, but where crew exposure during barrel changes would be tactically dangerous. The weapon's mechanical reliability, demonstrated conclusively in the Strensall trial but validated repeatedly in combat across multiple theaters and climate extremes, meant that tactical planning could assume weapon availability, focusing attention on ammunition supply and water management rather than contingency plans for mechanical failure. The MG-42, with its air-cooled quick-change barrel system and extraordinary cyclic rate ranging from 1,200 to 1,500 rounds per minute depending on specific model and condition, dominated in mobile operations requiring immediate, devastating suppressive fire concentrated in brief periods. Its tactical employment philosophy emphasized rapid displacement, multiple firing positions, and coordinated fire and movement between weapons in the same section. The high rate of fire created devastating psychological effects. The characteristic buzzsaw sound became instantly recognizable and feared by Allied soldiers, and could suppress enemy positions within seconds, enabling German infantry to maneuver, assault, or disengage. The barrel change system, while requiring interruptions in fire, enabled the weapon to sustain higher overall firing rates than would be possible with a fixed barrel, provided crews maintained discipline regarding barrel temperature management and had sufficient spare barrels available in the position. However, technical specifications alone tell only part of the comparative story and miss crucial context. The Vickers was embedded in a comprehensive system that extended far beyond the weapon itself. Industrial production infrastructure capable of delivering billions of rounds of rifle-caliber ammunition annually from factories distributed across the British Empire. Specialized training establishments like Hythe and Netheravon that taught systematic fire planning with mathematical rigor. Formal doctrine codified in training pamphlets and field service regulations that treated machine guns as area, effect weapons requiring coordination at battalion level, and logistic systems that included specialized equipment for water condensation, standardized spare parts distribution, and integrated ammunition supply chains. The weapon's effectiveness derived not primarily from superior engineering, though the design was certainly sound, but from this comprehensive integration of weapon, ammunition, training, doctrine, logistics, and organizational structure. The MG-42 was similarly embedded in its own supporting ecosystem. German tactical doctrine developed through extensive combat experience on the Eastern Front that emphasized squad-level autonomy, fire and movement tactics, and flexible response to fluid battlefield situations. Training that perfected rapid barrel change drills until they became nearly reflexive under stress, and employment concepts that integrated the weapon with other squad elements including riflemen providing security during barrel changes, ammunition carriers ensuring constant supply, and assistant gunners managing spare barrels and monitoring weapon temperature. The weapon's tactical effectiveness was as much a product of German small unit leadership, tactical proficiency, and combined arms coordination as it was of the weapon's technical parameters. The human dimension, often abstracted away in technical comparisons, cannot be separated from mechanical performance. Gun crews on both sides endured extreme conditions that tested physical endurance and psychological resilience. British Vickers teams managed water supplies and ammunition belts across missions lasting many hours, maintaining fire discipline and mechanical maintenance standards while exposed to enemy fire, environmental extremes, and the accumulated fatigue of sustained operations. The physical labor involved was substantial. A full ammunition box weighed over 30 pounds, water cans added more weight, and the gun itself with its tripod mount approached 100 pounds of equipment that had to be moved, placed, maintained, and if necessary displaced under fire. German MG teams executed barrel changes under fire while managing the tactical and physical challenges of handling metal components heated to dangerous temperatures, tracking barrel rotation sequences to prevent premature barrel failure, and coordinating with other squad members to maintain security during the vulnerable moments when the gun was briefly out of action. Both sets of soldiers demonstrated remarkable technical proficiency under combat stress. The historical record preserves specific achievements. Highwood's 1,000,000 rounds over 12 hours, demonstrating organizational coordination. Strensal's 5,000,000 rounds over 7 days, demonstrating mechanical endurance. The Sangro Barrage, demonstrating tactical innovation. The Gothic line operations, demonstrating sustained operational pressure. These events were not isolated technical demonstrations but integrated components of larger campaigns where multiple factors, logistics, intelligence, terrain, weather, morale, intersected to determine outcomes. What emerges from the documented evidence is that machine gun effectiveness in the Second World War was fundamentally about integration and sustainability. The most technically impressive weapon could fail if logistics couldn't sustain it, if doctrine didn't employ it properly, or if training didn't prepare crews adequately. Conversely, a weapon with modest technical parameters could achieve remarkable results when integrated into effective systems. The Vickers and MG42 represent two valid approaches to the same problem: how to deliver sustained automatic fire in combat. The British solution emphasized endurance through cooling. The German solution emphasized intensity through rate of fire. Both worked within their design parameters and operational contexts. The post-war years saw both designs influence subsequent weapon development. The Vickers remained in British service into the 1960s, including the Strensal trial that validated its mechanical durability. The MG42's design influenced the American M60 machine gun and remains in production today as the MG3. Modern weapons incorporate elements from both philosophies: quick-change barrels for thermal management, sustained fire capability for area suppression, and system integration with advanced optics and ammunition types. The mathematics of fire, the calculations of cooling water, barrel temperatures, ammunition consumption, and logistical burden may seem abstract when recorded in technical manuals and after-action reports. But these numbers represented life-and-death realities for soldiers who operated, maintained, and fought with these weapons. Each round fired, each barrel changed, each pint of water added or recovered was executed by human beings under extreme stress and danger. The Vickers crews who placed their guns at Sidi Rezegh, who plotted indirect fire across Italian valleys, who sustained night-long harassment missions, they transformed engineering specifications into tactical effects. The MG42 teams who changed barrels under fire, who maintained devastating fire rates during counterattacks, who operated in defensive positions against overwhelming Allied material superiority, they extracted maximum performance from their weapons despite resource constraints. Both sets of soldiers merit respect for technical proficiency under combat stress. The historical record preserves these events not to glorify war but to understand it. The technical analysis of weapon systems, logistics networks, and tactical doctrine serves a purpose beyond military history. It reveals how human organizations respond to extreme challenges, how industrial societies mobilize resources, and how technical decisions cascade through systems to produce operational outcomes. The Vickers versus MG42 comparison is ultimately not about which weapon was better but about how different societies approached the same problem with different solutions, each valid within its context. The veterans who served these weapons are passing into history. The battlefields where they fought are now quiet, but the lessons remain accessible through documentation: unit diaries, technical manuals, after-action reports, prisoner interrogations, logistics records, and engineering studies. These sources allow reconstruction of events and assessment of decisions with greater clarity than was possible during the chaos of combat. They permit evaluation free from contemporary propaganda while maintaining respect for the participants' experiences. The water versus air cooling debate in machine gun design has largely been resolved in favor of air cooling with quick-change barrels, primarily due to weight considerations for modern mechanized warfare. But the Vickers' sustained fire capability remains relevant in certain tactical scenarios, particularly for fixed defensive positions and vehicle mounts where weight is less critical. The principle it embodied, that endurance can be engineered through thermal management, continues to influence weapons design. Similarly, the MG42's high rate of fire established expectations for suppression capability that modern weapons must meet or exceed. The final assessment must acknowledge both what the evidence shows and what it cannot reveal. The documented facts, firing rates, cooling capacities, ammunition consumption, barrel lives, are accessible and verifiable. The human experiences, fear, exhaustion, determination, loss, are preserved in memoirs and oral histories but resist quantification. Both dimensions are essential to historical understanding. The Vickers and MG42 were tools designed by engineers, employed by armies, and operated by soldiers. Their effectiveness was a product of all three factors. This documentary narrative has attempted to present the technical and tactical dimensions with accuracy, while maintaining awareness that behind every statistic were human beings whose service and sacrifice warrant remembrance and respect. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.